Still on eigenvalues and eigenvectors, we now go to look at the idea of diagonalization of matrices. Diagonalization of matrices. So, straight up, a square matrix A is diagonalizable if it can be written as A equals PDP inverse, where D is a diagonal matrix. Of course, this is what a diagonal matrix looks like. A matrix that has only a non-zero element on the principal diagonal. Then P contains eigenvectors as columns. So P now, the columns of P are eigenvectors. So we already know what eigenvectors are, right? Like in the previous video, in fact, the last two videos, I mean, in the first video on eigenvalues and eigenvectors and the one after it, we looked at the process of getting eigenvectors like that. So, P square matrix A is diagonalized if it can be written as this. P contains eigenvectors as columns, and P inverse is the inverse of P, basically. So, if you can write any matrix A as PDP inverse, where D is is a diagonal matrix and P has eigenvectors as its columns, and P inverse is the inverse of that P. Then you have that. So, like I said, the diagonal matrix has the form D, where you have the eigenvalues lambda 1, lambda 2, lambda 3 along the principal diagonal of D. So the diagonal entries are eigenvalues for this particular D. So we see that D is a diagonal matrix with eigenvalues as its elements, as its non-zero elements, which are along the principal diagonal, while P contains eigenvectors as columns. So you have an interplay of eigenvalues and eigenvectors right here. So now the question is, why? Why is diagonalization useful? So here we are seeing why diagonalization is useful. Diagonalization helps us to compute powers easily. Instead of having to say a raised power n, where you want to multiply matrices and you have to say a times a times a times a many times, instead of using that, you can just straight go to use diagonalization, where you can say, since you can write a as p times d times p inverse, then a raised power n is simply just increase the power of d easily. And to raise a diagonal matrix to a power is very straightforward. So for a diagonal matrix, having lambda 1, lambda 2, lambda 3, or some lambdas along its principal diagonal. So the d raised power n is simply those diagonal element raised to power n easily, right? So that makes raising matrices to powers pretty swift and sweet. Now, another thing is that diagonalization helps us to solve differential equations. Imagine that for systems x prime equals ax, like that. Diagonalization simplifies the solutions to this because you can then write a as PDP inverse, and that makes it easier to solve. Then it can also help us to analyze systems like systems used in physics, economics, population models, and engineering. So diagonalization can help us do that. Then to also help us also to understand structure. So this shows how a matrix scales space in special directions. So let's go again to look at eigenvalues and eigenvectors, because already a matrix A is diagonalizable, right? Like we've seen already, if you can express the matrix A as PDP inverse, okay? This is diagonal matrices, diagonal matrix of eigenvalues, if you like, diagonal matrix of eigenvalues. So you see eigenvalues playing out here, whereas P is a matrix of eigenvectors, matrix of eigenvectors. So of course, the inverse of P is just this same P, the inverse of that matrix of eigenvectors. So that's why we can't talk about diagonalization without talking about eigenvalues and eigenvectors, right? So talking about eigenvalues and eigenvectors, now to diagonalize A, we need eigenvalues and eigenvectors. So the first step is you want to find eigenvalues the way we usually do them. Take the absolute value of A minus lambda I equated to 0. So you solve that. This is the characteristic equation. Step 2, find the eigenvectors. We already know how to do that. So for each eigenvalue lambda, solve this to find v, the eigenvector. So we are looking for non-zero solutions, which are eigenvectors. Then another question that arises is, when is a matrix diagonalizable? When do you say a matrix is diagonalizable? An n by n matrix is diagonalizable if it has n linearly independent eigenvectors. That is, if no eigenvector is a multiple of the other, you know. So we say that you have uh so you can say that the matrix is diagonalizable. Practical rule: if you have n distinct eigenvalues, it is diagonalizable. So I remember in the last video, we had a case where we looked for the eigenvalues of a particular matrix, and two of the eigenvalues are the same. So in that case, you cannot diagonalize that kind of matrix. So what if you have n distinct eigenvalues? Yes, you can diagonalize the matrix. If you have repeated eigenvalues, maybe, but no guarantees. Then if you have not enough eigenvectors, then that's totally no, right? But the sure thing is, if you have n distinct eigenvalues, then you can diagonalize the matrix. So imagine this now. Uh, we have some definitions right here. We talk about algebraic multiplicity. So algebraic multiplicity is the number of times an eigenvalue appears. Like that case where he had lambda minus 4 into lambda minus 2 squared. So number of times an eigenvalue appears. So 4 appears once, but 2 appears twice. So that's algebraic multiplicity. On the other hand, we have geometric multiplicity, which is the number of independent eigenvectors. So the fact that an eigenvalue appears a number of times does not necessarily correspond to you having that number of independent eigenvectors. So, uh, so number of times an eigenvalue appears plus the geometric multiplicity is the number of independent eigenvectors, and they always satisfy the fact that geometric multiplicity is always less than or equal to algebraic multiplicity, right? So, if you have if an eigenvalue appears a particular number of times, then the number of independent eigenvectors will be less than or equal to that. So, and they are good. So, if geometric multiplicity is equal to algebraic multiplicity, then you can say the matrix is diagonalizable. So equality of geometric and algebraic multiplicity implies that the matrix, such matrices producing those are diagonalizable. So then we talk about general procedure for diagonalization. So, given a matrix, they find eigenvalues from it by looking for the determinant of A minus lambda and equating to 0 and solving. Then find eigenvectors by using standard procedure A minus lambda IV equals 0. Then check linear independence, right? Check if the eigenvectors are linearly independent. Then form P using eigenvectors as columns. So the eigenvectors you would have got here. So put all the eigenvectors together. That's P automatically. Form the using eigenvalues on the diagonal. So the eigenvalues we'd have got here. So put them on the diagonal of D. Then compute P inverse. That maybe that's the next thing. That's the next serious business. So compute the inverse of P. And then once you have that, you can then say that your A is equal to PDP inverse, basically, right? So let's go for a very nice case. So here you want to diagonalize A, which is 4102. We already know how to find eigenvalues, right? That's determinant of A minus lambda I. That will be 4 minus lambda, 1 minus 0, that's 1, 0, 2 minus lambda. So if you multiply that, you have 4 minus lambda, 2 minus lambda equals 0. So lambda 1 is 4, lambda 2 is 2. You can also say lambda 1 is 2 and lambda 2 is 4, whatever. Then we have got eigenvalues. So let's go for eigenvectors now. So for eigenvectors, if you start with lambda 4, so A minus lambda 4i, that means A minus 4 times I now. So here we have, this will be 4 minus 4, we have 0. Then this is 1 here, this is 0. 2 minus 4, minus 2. Okay. Then solution, y equals 0. So in this case now, we just have 0y equals, I mean, if we talk about V1, V2, if you use V1, V2, so 0, 1, V1, V2. So V2 is 0, 0 minus 2. V2 is still 0. So V2 is given as 0, but we don't know V1. That's X now. X is not known, but Y is given to be this. So it means that the vector will simply be 1, 0, like that. The eigenvector is 1, 0, because Y is known based on what we see from here. Now, this is what I'm describing. So you have 0, 1, 0 minus 2, right? So you have 0, 1, 0 minus 2 against what I would call V1, V2, but to avoid the confusion with that one now. So it's more like just saying X and Y, basically, and all of this equals 0. So if you do all this now, so two rows, right? So write this twice. So X, Y, X, Y. So that means 0, 1, 0 minus 2. All of that is equal to 0, 0. So from here, we know that Y is 0 and minus 2y is 0. Everything together tells us that, so if you put everything together, it simply tells us that y is equal to 0. So y is known, but we don't know x. X it doesn't show up. So in that case, the easy thing to do is just say let x be equal to 1. So finally, we have xy, which is equal to 1, 0, because y is conclusively 0. So that means this is our vector right now, 1, 0 in that case. So that's the vector corresponding to 4. You have to do for lambda 2 also. So for lambda 2 now, if you do a minus 2i, so it's more like you now have this 4 minus 2. You have 2 here. Then you have this one. Then 2 minus 2 is 0. So at the end of the day, um you just have 2x plus y. So this is what's happening here now. So so it's like you have 2100, then xy. Okay, 2100 xy. So this is 2100 with xy. Again, you do the same thing, and all of this is equal to 0, 0. So you do the same thing, right? So you have two rows here. So write this twice. So xy, xy. So this is 2, 1 up here, then 0, 0 here. And all of that is equal to 0, 0. So what happens? You have 2x plus y is equal to 0, right? So these ones are wasted, so to speak. So here you just have y is equal to minus 2x. So I mean, we don't have to do too much, because here we already know that whatever x is, y will be twice of that. So we can then say xy is such that if you pick x to be 1, y will just be minus 2. Okay, so that'll be 1 minus 2 like that. So this is 1 minus 2. So you can then build P and D. So for P, P is the matrix of the eigenvectors. So the first eigenvector was 1, 0, like we got here. So V1, you put it here, that's 1, 0. V2, 1 minus 2, you put it here, that's P. Then for D, you have 4, 0, 0, 2, right? For the one eigenvalue. You can also have 2, 0, 0, 4. Anyhow you do it is fine. Okay. Then the result now so at the end of the day, you have your A. A can be written as A PDP inverse. So I mean, and that means the matrix is diagonalizable. So I mean, you may just want to go the extra mile, right? Okay, well, I mean, we have okay, maybe I just want to do that setup. So let me do the setup just to show all that. So we have A already. What's that A again? I think I need to remember that. A is 4102. That's the original A. It's 4102. A is 4102. 4102. Because it is a triangular matrix already, we can already see that lambda 1, lambda 2 is equal to 4 comma 2, if you like. Those are the eigenvalues. Then we also know that eigenvectors v1, 1 we got to be 0, 1. V2, we got another one to be 1 minus 2, if you remember that. Okay, I even did that on this same page. Yeah, we got one to be 1, 0, and this is 1 minus 2. So we have this already. So we have this like this. What else do we need to know? We also have so it means that we can get the diagonal matrix D to be, it is the matrix of eigenvalues. So this is lambda 1, 0, 0, lambda 2. So this is simply 4, 0, 0, 2. Or if you like 2, 0, 0, 4, anyhow. Then P, on the other hand, now P should be the matrix of V1 and V2. So that's simply V1 is 1, 0. V2 is 1 minus 2. V2 is 1 minus 2. Okay. So also we can say that P inverse, we can get P inverse. This is a 2 by 2 matrix, so it's easy. So the determinant of this now for P inverse, the determinant of this is the term 1 over determinant of P into um okay, I mean, we can go straight. The determinant here is simply minus 2. You know, that's minus 2 minus 0. So that's minus 2 into, uh, we switch 1 and minus 2. So this is minus 2 here. This is 1 here. Then this 1 and 0 will remain. So this will be minus 1. This will be 0. Okay? So if we divide through, so we have P in, if we multiply through by minus half now, we just simply have, this is 1 here. This is 1 over 2. This is 0. And this is minus 1 over 2. Okay? So this is minus, yeah, I think so. So yeah, this is 1, this is 1 over 2, this is 0, this is minus 1 over 2. So in all, now we can say that A is equal to PDP inverse. That means that the original A we started out with is 4102, right? So we have 4102. So that means we can say 4102 is the same thing as P. What is P now? P is 10 half minus half. 10 half. No, this is P inverse. P itself, sorry, P itself is 101 minus 2. So this is 101 minus 2, okay, into D, which is 4002, and P inverse finally is this expression here. So 1 half, 0 minus half. This is 1 half, 0 minus half. Okay, so 4102 can exactly be written like this. So you may be curious, you want to check, is that really true? So we can do a quick check, right? We can multiply this out first. So I'll just do the sharp, sharp thing. So 2 rows, right? So I have 1, 0, 1, 0, then half minus half, half minus half. So I put this 40 over this. So this is 40 and this is 40. Then down here we have 02 and this is 02. So we have that side, you know, waiting. And then for this other one, we have 110 minus 2, 110 minus 2. So let's study this up first. So this implies that we have 1102 multiplied by so this is 4 right there. This is half of 4 is 2. Half time minus half times 0 is gone. This is 0 down here. This is half times 0. So everything is 0 here. So again, we go for the next level. So these two things together multiplied. So it means we have okay, 2 rows again, multiplied it 2. We have uh so write the columns twice each. So you have 4040, then 2020, then put 1 over this, 1 over this. This is 02, this is 02. So that means this is the same thing as 4 times 1, there is 4, 2 times 1 is 2. This is 0 here. This is this is 02 here. Seriously? Something is not right. If we are expecting 41, right? 4102. Something is not correct. Mm, something should be wrong somewhere. Okay, again, I go again. This is 10, half minus half. So 1 half, 0 minus half. So 10, half half. So this is 4040. Aha, this is the challenge here. So this is actually 2 here. So uh this is 4040. This is 0202. So actually here this should be minus 1 here. That was the fault there. So minus half. So now 4040, and this should be 2 minus 1, 2 minus 1. Yeah, 2 minus 1, 2 minus 1. Okay, now I think we are good. So this is 4, 2 times 1, 2, 2 minus 1. This is 1 right here. This is 1 here. 4040. So this is 20. So minus 2. This is minus 2. I feel something is still wrong again. So this is 4040. 2 minus 1, 2 minus 1. Uh, 2 minus 1, 2 minus 1. So this is 0. This is minus 2. That should be plus 2 actually. So let's see again what's wrong with that still. 1, 0, 1 minus 2. 1, 0, 1 minus 2, yes. Then this is 4, 0, 0, 2, yes. And for the inverse, 1 half, 0 minus half. Did I do that correctly? So switch over my, aha, you see, this is, so if, okay, yeah, we switch it, that's fine. And this is minus 1, 0, yeah. Then we have 1 half, 0, yes, and this is minus half. Okay, so 1 half 0 minus half. So again, 1 0 1 0 half minus half half minus half. So put 4 0 4 0, yes, 0 2 0 2. So then we have this is aha. Okay. Yes. See, silly mistakes. This is minus 2 here, right here. Yeah. So this is 1 1 1 1 0 0 minus 2. So 0 minus 2 0 minus 2. Okay? So this is 4 0 4 0 2 minus 1, 2 minus 1. Then 0 minus 2, 1 1 up there, 1 1 up there. 0 minus 2, 0 minus 2. Okay. So finally, I think we are good now. So 4 times that, that's 0, 2. So this is 2. Yeah. So you see, we can actually express 4102 as this whole thing. So that really makes sense. Okay. So that works. So you have to be careful of all the uh, minus the plus here. So that's how to diagonalize the matrix pretty easily. Okay, so now the first one we did was for when we had distinct eigenvalues. So in this case, now 4 and 2 are the eigenvalues. You could even have read it off from here directly because it's an upper triangular matrix. So what about for repeated eigenvalues? So in this case now, from this alone, this is upper triangular matrix. So this one is going to have eigenvalue 3 as eigenvalue twice. Okay. So again, eigenvalues we have 3 minus lambda, 3 minus lambda. From here, we already know it's going to give us 3 minus lambda squared equals 0. So lambda is 3 twice. So it means we have eigenvectors now. That's a minus 3i. So you can always just come back. Oh, okay, we didn't do that here. So we are going to have 3 minus 3 0, 3 minus 3 0, and then we have 1 0. So in this case now, we have it straight that this is y is clearly equal to 0. So it means you just pick x to be 1. So in this case, now we have only one independent vector. We don't have more than one. So we cannot get the other one. So it means we have eigenvectors less than the dimension of the matrix itself. So in that case, we have only one independent vector, and we need at least two because the number of independent vectors must be equal to the dimension of the matrix, which is the 2 by 2 matrix. So the conclusion is that since two are needed, the matrix is non-diagonalizable. So in fact, once you have repeated eigenvalues, just know that you cannot diagonalize the matrix easily. Okay. So then computing the powers now, if you want to compute powers, this is example 3 now. So you want to compute powers of a matrix. So what do? So you see here that suppose A is PDP inverse, that is, you can diagonalize A, and D is 2003. So you want to find A raised power 5. So if you want to find the fifth power of A, basically just say the solution is A raised power 5 because PD raised power 5 P inverse. So if D is 2003, so D raised power 5 is simply 250035. And 2 raised power 5 is 32. 3 raised power 5 is 243. So to now find the A raised power 5 itself, you have P. So whatever P was, if you are given that P, so you multiply by this D raised power 5 and multiply by the P inverse, and you would have got the matrix to the fifth degree. Okay, well, do I want to do that with what? Okay, since we already have a clear case, and maybe I want to I want to demonstrate that, right? Um, okay, we already have a clear case. So maybe I have this question. Find what's the original matrix again? 4102. Find 4102 raised to power 5, right? So we know that 4102 raised to power 5 is the same thing as that what we had here. That is this whole expression, right? This 1 So we know that a raised to power 5 can be PD raised to power 5, P inverse, like this. We already know that. So in this case now, for us to pull this off, so we know P itself is P is 110 minus 2. P is 110 minus 2. Okay. Then all of that into D raised to power 5. D raised to power 5 means the diagonal matrix, this one 4002. Okay. So 4002 raised to power 5 into P inverse. P inverse is 1/2, 0 minus half. Okay, so this is 1/2, 0 minus half. Okay, so we can just tidy up all of this now. So this is 1, 1. This is 1, 1, 0 minus 2 into 4 raised to power 5, 0, 0, 2 raised to power 5 into 1/2, 0 minus half. Okay, so this is the same thing as 1, 1, 0 minus 2. 4 raised to power 5 is okay, that's 4 times 4 times 4 times 4. Uh that's a lot. But it's okay, we can pull it off. 4 raised to power 5. So this is 4 raised to power 5. And that is 1024. This is 1024. So that's actually 2 raised to power 10, right? That's 2 raised to power 10. That's 10240. 2 raised to power 5 is 32 into 1/2, 0 minus half. Okay? So then we can tidy up this part first. So we can leave this alone. This is 110 minus 2. So I have to do this carefully now to avoid all the usual troubles. So this is 2 rows now. So I need to write this each one twice. 10, 10. Then half minus half. Half, half minus half. Half minus half. Okay? And then we put this over it, over the top. That's 10240. Then 10240. Then down here we have 032, 032. Okay? So carefully we have 110 minus 2 into, so this is 1024 up there. Head half of this, that's 512, I believe. Yeah. And this is of 0. So this is 0 down here. And this is minus 16 here, I think. Yeah, that's minus 16. So next, we can then tidy up further. Again, 2 rows. We write each column twice. So we have 10240, 10240. Then this is 512 minus 16, 512 minus 16. So, and then we can take this up 1, 1, 1, 1. This is 0 minus 2, 0 minus 2. So easy peasy. That means that 4102 raised to power 5 now is going to be this result. 4102 raised to power 5 will now be, this is 1024, yeah, and this is 516 minus 16. That is 500, I believe. Yeah, that's 500. And this is 0 right here. And this is 32 right here. So, and we can quickly check that this is 1024, 532, like that. So let's see what that happens to be like. 4102 raised to power 5. Okay. Let me see if we can okay, maybe let me use Wolfram alpha in this case. Wolfram alpha, talking about matrices. So matrix exponential. Yes, I like this. Matrix exponential. Matrix exponential. Okay, 4102 raised to power 5. Matrix. This is, I can just do this now. 4, 1. How did we do that again? Let me see. I think it's like this. Aha, yeah, something like this. 4, 4, 1, 0, 2 raised to power 5. Raised to power 5. Yes, that's okay. This is 496. Okay, so 1024. So it's only that 496 that is wrong. Why? This is 516, right? What did I do wrong here? 1024. Oh, sorry, this is 512, chai. 512. This is 512, yes. So 512 minus 16. So 12 minus 6 is 6. 0 here. 10 minus 1, 9. This is 496. Okay. This is 496 actually. So you can see very prone to silly mistakes. So now, can you imagine if you have to do 4102? So normally what we should have done was, I mean, if we didn't have this fast way, so 4102 raised power 5 would have just been 4102 multiplied by 4102 multiplied by 4102 multiplied by 4102 multiplied by 4102. That's going to be a lot of stress. But by doing it this PDP way, PDP inverse, PD5, P inverse, so you get your result straight up and life goes sweet. Okay. So that's really very useful right there, like that. Okay. So we go back to our notes. So we see that helps a lot. So we have special cases of symmetric matrices, right? If A transpose is A, then A is symmetric, right? So real symmetric matrices are always diagonalizable. So the real symmetric matrices are diagonalizable because they satisfy that A is equal to Q D Q transpose, where Q is orthogonal, right? So this is used in physics and data science. So Q D Q transpose instead of P D P inverse. So we have Q D Q transpose because Q is an orthogonal matrix. So the question is, why diagonal? So we ask ourselves, why does diagonalization matter, right? Why is it useful? What are the applications? What's the importance? First of all, like we've seen already, it simplifies problems. It turns hard matrices into easy ones, like the one we just did, trying to raise a matrix to power 5. Then long-term behavior for systems like x of n plus 1 equals axn, largest eigenvalue controls the growth at the end of the day. Then we have its application in engineering and science. It is used in vibration, circuits, quantum mechanics, and heat flow. So in machine learning, it is used in principal component analysis and covariance analysis, which I talked about, I think, in the very first video under eigenvalues, values, and eigenvectors. Then for mathematical insight, it shows that matrices act like scaling in special directions. So there are some common mistakes too. Forgetting to check independence. You want to be sure the matrices, I mean the eigenvectors are not dependent. Okay, if they are dependent, that is one is a multiple of the other, then there's no point. And assuming repeated eigenvalues always work. So the fact that you get a repeated value doesn't mean that it always work. Mixing eigenvalue order in P and D. So that won't so if you make sure the first eigenvalue you use in D must correspond with the first eigenvector you use in P. That is, don't use like the other time I did 4002. So uh the first eigenvector in P must correspond to 4, while the second one corresponds to 2. If I had done 2004, I have to reverse the eigenvalue. So that's very important. Then forgetting that P must be invertible. So don't forget that if P cannot be invertible, you can't find the inverse of P, then that doesn't work. Okay. So let's talk about some diagonalizations checklist. In summary, find eigenvalues, find eigenvectors, check independence, build P, build D, and compute P inverse. So that in that way, we can then diagonalize our matrix as this, that A is PDP inverse. And if you want to raise A to any power, you can then just raise the diagonal to the power, multiply out, and you get the matrix. So the main idea is that diagonalization turns complicated transformations into simple scaling. So we have some problems we can handle here. So solve each problem carefully. Show all steps. 2005 diagonalize. Diagonalize 1221. Then diagonalize 3103. Determine whether A is diagonalizable. Well, I can see that it is not diagonalizable because it has repeated eigenvalues. So that won't help anything. So here this should be diagonalizable because 421 are different. Then yeah, this most likely should be diagonalizable. Then problem 6 now, 2112 again, use diagonalization to find a raised to power 4. Then problem 7, find a raised power 6 using diagonalization where 3012 is what you have there. Then determine whether the matrix is diagonalizable. It is not diagonalizable because I can already see that the eigenvalues are the same, you know. Then yeah, diagonalize. You want to diagonalize this. Well, I mean, well, this is suspicious. It's suspect because of, okay, well, it is not a triangular matrix, so you have to just go through the process. And here we have problem 10, diagonalize a, find an in terms of n, like that. Yeah, so maybe I should do this last one and then call it and end it here. So 6 minus 213. So a 6 minus 213. 6 minus 213. That's what a is. Okay, so we have a is 6 minus 213. So we want to diagonalize, That means we want to write A as PDP inverse, where D is the matrix of diagonals of eigenvalues, and P is the matrix of eigenvectors. Maybe I should write that. It's really important. D is diagonal matrix, diagonal matrix of eigenvalues, diagonal matrix of eigenvalues. Then P is matrix of eigenvectors, and they have to be corresponding with the eigenvalues of the, of course, P inverse is just the inverse of this. So with that in place now, we need to find eigenvalues, eigenvectors. So to find eigenvalues, we know we need the determinant. We need the determinant of a minus lambda I equals 0, and we equate to 0 and solve. So we have 6 minus 213. So that's 6 minus 213 minus lambda into 1001 equals 0. So we do all this. This is 6 minus 213 into, minus lambda 0, 0 lambda equals 0, 0. Okay, like equals 0 because it's determinant, right? So that means we have 6 minus lambda minus 2, 1, 3 minus lambda equals 0. So we find the determinant. That's 6 minus lambda into 3 minus lambda minus 1. Okay, minus 1 into minus 2. That's this times this minus this times this equals 0, like that. So we can expand now. We have 6 times 3 is 18, minus 6 lambda minus 3 lambda plus lambda squared plus 2 equals 0. So that's lambda squared minus lambda squared minus 9 lambda, okay, minus 9 lambda, 18 plus 2, that's plus 20 equals 0. So we need to factorize. Two numbers multiply, you get 20. Add, you get minus 9. That should be minus 4 minus 5, I believe. So that's lambda. So this is now the characteristic equation we need to solve. So this is characteristic equation. Okay, as characteristic equation. So the next thing now is to solve this now. So we have lambda squared minus 5 lambda minus 4 lambda. That gives minus 9 plus 20 equals 0. So we have lambda squared minus 5 lambda minus 4 lambda minus 20 equals 0. So this is lambda into lambda minus 5 minus 4 into lambda minus 5 equals 0. So we have lambda minus 5 into lambda minus 4 equals 0. So that means that lambda, you can see lambda 1, we have lambda is equal, minus 5 is 0, or lambda minus 4 is 0. So we have lambda is 5 or lambda is 4. So we can say, therefore, lambda 1, I like to arrange, lambda 1 is 4, lambda 2 is 5. So we have our eigenvalues, right? So we now need to find the eigenvectors. So to find the eigenvectors, So we start for lambda 1 equals 4, right? We know that should be a minus lambda I into v equals 0. So again, we have, what is a now? 6 minus, what's that now? 6 minus 2, 1, 3, yeah? 6 minus 2, 1, 3, minus, so the first lambda is 4 here. So we have 4 into 1, 0, 0, 1. All of this into v1, v2 equals 0, 0, like this. So that this is now 6 minus 2, 1, 3, minus 4 into 0, 0, 4, like this. This v1, v2 equals 0, 0. So that this is now, this is minus, by the way. So 6 minus 4 is 2. We have minus 2. 1 minus 0 is 0. 3 minus 4 is minus 1, I think, into v1, v2 equals 0, 0. So we can expand this now. So to expand this, we know 2 rows. So we write this twice. So we have v1, v2, v1, v2. So that is 2 minus 2, 2 minus 2, right? So, okay, this is 1 minus 0, 1, sorry. 1 minus 0 is 1. Then 3 minus 4 is minus 1, yeah. So that's 2 minus 2, 1, 1 minus 1. And that is equal to 0, 0. So at the end of the day, we have 2v1 minus 2v2 equals 0. So if you divide through by 2, this implies that v1 minus v2 equals 0. For the other one also, this other one is v1 minus v2 equals 0. So you can see they are fundamentally the same thing. So that means that v1 is equal to v2. So if v1 is equal to v2, we can simply say that v1, v2 is just when v2 is 1, v1 is also 1. So we can put that together. We have for determinant 4, for eigenvalue 4, the eigenvector is 1, 1. We have that. So then we go again for the other one. So we say for lambda 2, which is equal to 5. Remember, lambda 2 is 5. We got two lambdas. Lambda 1 is 4, lambda 2 is 5. So for lambda 2, which is equal to 5, what do we do? Again, we have lambda a minus lambda I, okay, into v multiplied by v is equal to 0. Okay, so again we do the same thing. So we have a 6 minus 1. I keep forgetting what that is. 6 minus 2, rather, 1, 3. 6 minus 2, 1, 3, right? 6 minus 2, 1, 3. 6 minus 2, 1, 3. 6 minus 2, 1, 3, minus the lambda now is 5 into 1, 0, 0, 1 equals 0, 0. Okay, we have v with this. So v1, v2 equals 0, 0, right? So this is 6 minus 2, 1, 3, minus 5, 0, 0, 5 into v1, v2 equals 0, 0. So next we have 6 minus 5, that's 1, minus 2 times 0. Oh, minus 2 minus 0, that's minus 2. 6 minus 5, 1 minus 0 is 1. 3 minus 5 is minus 2 again. So we have this into v1, v2 equals 0, 0. So we have two rows here. We have one column. So write the one column twice. So we have v1, v2, v1, v2. So we have 1 minus 2, 1 minus 2. So, and this is equal to 0, 0. Fundamentally, they are exactly the same. So v1 minus v2, v1 minus 2v2 is equal to 0. So same, this one to v1 minus 2v2 is equal to 0. So fundamentally, the two of them simply tells us that v1 is equal to 2v2. Okay? v1 is 2v2. So, so it means that if v2 is equal to 1, v1 is automatically 2, right? So if v2 is equal to 1, v1 is equal to 2. So this implies that v1, v2 is in the ratio 2 to 1. So what else? And that simply still means that for eigenvalue 5, we have the eigenvector 2, 1. Okay. So interestingly, we have we have 4, 1, 1, and then 5, 2, 1. So overall, we have 4, 1, 1, and 5, 2, 1, and 5, 2, 1. So uh this is lambda. Okay, let me do it this way. Overall, lambda 1 is equal to 4, and v1 is equal to 1, 1. Lambda 2 is equal to 5. V2 is equal to 2, 1, right? Um, um, V2, right? V2 and V1 are independent, right? V2 and V1 are independent in the sense that if V2 was 2, 2, or V2 is also 1, 1, then we only have 1, 1, right? But V1 and V2 are independent. So, so, um, so we have, so we can have, let me say we can have, so we can have A to be equal to PDP inverse. We can have it to be PDP inverse such that P now is the, or maybe we can start with D. So we can have D to be the matrix of the determinants. So D now is equal to lambda 1, 0, 0, lambda 2. So follow the order. So lambda 1 is 4 here. So we have 4, 0, 0, 5. Very important. But if your lambda 1 is 5 and lambda 2 is 4, so make sure you follow the order like that. So you could also say 5, 0, 0, 5. Very important. But the other part is that for P now, you want to also be sure that, so for P, make sure if you use lambda 1 as 4, don't come and use your V1 as V2. Don't switch. Make sure lambda 1 corresponds to lambda 1. So since we started with 4 here, this will have to be V1, V2. So that for lambda 1, you have V1. For lambda 2, you have V2. So if you switch V2, V1, yeah, you're going to have issues. So for lambda 1, we have 1, 1, right? And for lambda 2, we have 2, 1, based on what we have up there. So 1, 1, 2, 1. So we can say that our A is 6. A, which is 6 minus 2, 1, 3. All right. A is 6 minus 2, 1, 3. Can be written as, of course, we know P inverse will just be the determinant of this. That's 1 over 1 times 1, 1. That's 1 minus 2, which is minus 1, into switch it over. So you have 1, 1. I mean, switch 1, nothing changes. Minus 2, minus 1. So if you put the minus 1 inside, you just have minus 1, 2, 1, minus 2, right? So yeah, switch all this over and change the signs, right? I hope I've not messed this up. Yeah, we have the determinant here. So switch over the numbers. So it's 1, 1. So whatever happens. So if you put the minus inside now, so you have minus 1, 2. So 1, 2, 1, 1. What's the determinant? I just want to be very sure of that. 1, 2, 1, 1. Determinant. This always helps, right? Determinant. Determinant of 1, 2, 1, 1. I know I have a strong feeling it is correct. I want to be very sure. Determinant. So the determinant is determinant. Oh, is that determinant? I'm looking for inverse, sorry. I was wondering. Inverse, inverse. Yeah, inverse. Minus 1, 2, 1, minus 1. Minus 1, 2, 1, minus 1. At the end of everything. Yeah, minus 1, 2. Minus 1, 2, 1. Yeah, 1 minus 1, sorry. Minus 1 to 1 minus 1. Yeah, because, yeah, minus 1 to 1 minus 1. Yes, so with that in place now, we can then say so 6 minus 1, 6 minus 2, 6 minus 2, 1, 3 can then be written as P, which is 1, 2, 1, 1, 1, 2, 1, 1, into D, that is 4, 0, 0, 5, into 1 minus 1 to 1 minus 1. Okay, so if you, of course, you can check again like I did before. So we can check. So let's start with this. This is minus 1, 1, minus 1, 1, 2, minus 1, 2, minus 1. Then put this over 4, 0, 4, 0, 4, 0, 0, 5, 0, 5. Okay, we have this into 1, 2, 1, 1. So this implies that we have 1, 2, 1, 1. I'll just go straight. This is minus 4 here. This is 8. This is 5. This is minus 5. Then we do that once more. So we have minus 4, 5, minus 4, 5. This is 8 minus 5, 8 minus 5. Then we have 1, 2, 1, 2, 1, 1, 1, 1. So again, this is 10 minus 4, that is 6. Then 8 minus 10 minus 2. 5 minus 4 is 1. Then 8 minus 5 is 3. Yeah, so voila, that's what we get. 6 minus 2, 1, 3. So that actually works perfectly. So with that, we come to the very end of this interesting video um, about diagonalization, which helps to simplify a lot of things we do. So try your hands on the practice problems. Let's see how well you get the gist. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Okay. If you have subscribed already, I must thank you very much. If you haven't subscribed, the question is, what are you waiting for? Subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you also want to become a member of this channel by clicking on join. That gives you some special privileges. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.